we're going to talk about how to find the derivative of a parametric equation. Okay? So we know that a parametric equation is x equals some function in terms of t and y equals some other function in terms of t. So we'll call them x equals f of t and y equals g of t. If we want to find the derivative dy dx of this parametric, all we have to do is use the chain rule. So I think one thing that we did back when we were first starting to talk about these parametric equation was we were able to write them back into a regular rectangular Cartesian equation. So let's suppose that we could find a way to eliminate the parameter in one of the equations to come up with what y is equal to in terms of x. So we'll call that y equals capital F of x. Okay. Everybody okay with that? You think we could do that? We could, let's say, eliminate the parameter in this one so that we could turn this y equals g of t into some other function of x. And we figure out what t is over here, solve for t in the x one, and then plug it in over here. Yeah or no?
Yeah.
Okay. So then my question becomes, what is y? Well, y is g of t. So let's rewrite this, and this seems a little weird. Why am I going to rewrite y as g of t, even though I just got rid of that g of t? And f of x, well, that would be capital F of little f of t. And again, why would I want to rewrite this all back in terms of t when I just got it in terms of x, right? That's the question. Well, what are we trying to do? We're trying to take the derivative of capital F of x with respect to x. So if I were to take the derivative with respect to x of each of these sides, I should be able to do that, right? What is the derivative of g of t?
G prime t?
Should be what? Oh, sorry. I've written not what I wanted to do. Sorry. I want to take the derivatives of each of these things because they're in terms of t with respect to t. So what's the derivative of g of t with respect to t? Please. Yeah, it should be, yes, thank you, Wes. Should be dy dt, right? That's just dy dt. And then if I want to take the derivative of capital F of little f of t, that should be what? It should be the derivative of capital F, right? F prime of f of t times the derivative of little f of t, which is what? That should be dx dt, and that's the chain rule right there, right? This is using the chain rule to differentiate capital F of little f of t. And if I go back through here, what is f of t? F of t is just f of t is just
X.
x. So this becomes capital F prime of x times dx dt. Well, what's capital F prime of x? That should be dy dx, shouldn't it? So dy dx ought to equal dy dt divided by dx dt. And that's the chain rule. And that's how we can find the derivative with respect to x of a parametric equation. And the reason we want the derivative with respect to x is because this is still in the xy plane, and dy dx should still give us the slope of the line tangent to this parametric function. So far good or no?
Yeah.
All right. So that's going to be our goal, is to find dy dx for some parametric functions. It should be pretty straightforward. So we'll do that here for this one. So dy dx ought to equal dy dt over dx dt. And what's dy dt?
T.
Wonderful. And what's dx dt? That's right, 5 to the 4th minus 12t squared. And I could cancel out a t to give me 2 over 5 t cubed minus 12t. Good or no?
Good.
All right, and one thing we might note is that the derivative with respect to x of a parametric function is going to come out in terms of t for us, which is okay, because generally we're given a range of t values, and we need to do stuff in terms of t with parametric functions. Let's do another one. What's dy dt?
Cosine t.
Cosine t. And what's dx dt? 2t plus 1 over 2 root t. Good or no? If you want to get a common denominator and simplify that down, you can, but it's not necessary. Any questions or issues there?
No.
All right. Why don't you guys do this one? What should we get? What's the numerator? Derivative of e to the sine t ought to be,
e to the sine t times cosine t.
yeah. And our denominator ought to be 1 over t cubed minus 2 times the derivative of t cubed minus 2, which is 3t squared. So we ought to end up with t cubed minus 2 cosine t e to the sine t all over 3t squared. Good or no?
Good.
Muy bien.
No issues? Everybody's all right? All right. Should be pretty straightforward. So now what we want to be able to do is we want to be able to find the second derivative of a parametric function. So that means we need to take the derivative with respect to x of dy dx. I'm having trouble writing on my laptop screen today. Wow, as I try to write. Sorry. The derivative with respect to x of dy dx, which should be, what do we know about dy dx for a parametric function? It's all in terms of t, isn't it? So how do I take the derivative with respect to x of something that is in terms of t?
Implicit differentiation.
Implicit differentiation, or using the chain rule, right? So what does that end up becoming? I can take the derivative of it with respect to t, right? The derivative with respect to t of dy dx, but then what do I need to multiply that by?
dt dx.
dt dx, exactly. The derivative of t with respect to x. And dt dx is not something that we really have just sitting around to use. But if we're multiplying by dt dx, that would be the same as dividing by the reciprocal of that. So we could say that what we want really is the derivative with respect to t of dy dx divided by dx dt. And this should be the second derivative of any parametric. So it is not just the second derivative of y divided by the second derivative of x. It's the derivative with respect to t of dy dx divided by dx dt. And so that's very important that we remember this formula for finding the second derivative of a parametric. Everybody okay with that?
Yeah.
All right. So let's find the second derivative of t to the fifth minus 4t cubed over y equals t squared. So I think this is the one we already did, right? We already had dy dx from earlier. What was dy dx for this? It was 2 over
5t cubed minus 12t.
Right. Okay. And so if we want to find the second derivative, the first thing we have to do is we have to take the derivative of this with respect to t. So what is the second derivative? Or what is the derivative of that? It should be what? How do you take the derivative of that? You could use the reciprocal rule, right? The negative 2 times the derivative of this, which is 15t squared minus 12, divided by 5t cubed minus 12t squared. Good or no? So far? And what do we need to divide that by?
dx dt.
Dx dt, which is 5t to the fourth minus 12t squared. And what could I do with that? I could take a t out of that, right? And then I would get another 5t cubed minus 12t in there. So what should this end up looking like in the end? Negative 2 times 15t squared minus 12 over t times 5t cubed minus 12t cubed. Good or no?
Wait, if you divided by dx dt first and then took the derivative, would that make a difference?
What do you mean if you divided by dx dt first? Like, you mean you divided this by dx dt?
Yeah, and then
Yeah,
took
it
the
would give you-
derivative.
Yeah, it'll
Oh.
give you a different answer. Yeah. You gotta do the derivative first and then divide by dx dt. Any other questions on this or no? Everybody okay with that? All
And then
right.
couldn't you factor out another t from the? Oh, and
From the denominator?
yeah, I looked at it wrong. The top is 15. Yeah.
Yeah, I mean, I could factor out a t from the denominator if I wanted to as a t cubed. I mean, I could make this 5t squared minus 12 and then a t to the fourth out here, but that's not necessary. But if you want to,
Got it.
yeah, but yeah, that was a, that doesn't, that's a parenthesis, not a 15. So let's do another one. Let's find the second derivative of x equals sine squared t, y equals cosine t plus 2. So first off, we need to find the
First derivative.
first derivative. First derivative should be dy dt, which is negative sine of t plus 2 over dx dt, which is what? Should be 2 sine t times the derivative of sine, which is cosine t. And if we wanted to be extra smart about this, what can we do with the denominator of that?
Combine that into 2 sine of 2t.
How about just sine?
Oh, wait, yeah, just sine 2t. Whoopsie.
Yeah, that would be good because that would allow us not to have to worry about the product rule when we take our derivative of this, because we're still going to have to use the quotient rule to take the derivative of this, which is going to be a pain. And if we have the quotient rule with the product rule inside of it, that's even more of a pain. All right, what about our second derivative then? It ought to be the derivative of this divided by dx dt. So the derivative of this should be what? Sine 2t times the derivative of this, which is negative cosine of t plus 2, minus this, so that'll become a plus sine of t plus 2 times 2 cosine 2t all over sine of 2t squared. And that's our dt of dy dx. And then we need to divide that by dx dt. And what was dx dt? It was another sine of 2t. And so what can we end up doing with this? We should be able to turn the denominator into a sine cubed of 2t. And what does our final answer look like? Something like 2 cosine 2t times sine of t plus 2 minus sine 2t cosine of t plus 2 all over sine cubed 2t. I just flipped the terms of the numerator around so I didn't have a negative out in front, but if you left it the other way, that's fine too. Any questions or issues with that? Everybody okay with that? And why would we want the second derivative? Well, maybe because we know it shows us concavity, right? So we might want to be finding the concavity of this parametric function. Everybody good? Any questions, any issues, any problems with that? Or are we all right? You all still there?
Yes, we're good.
All right. Okay. It's like I thought that one was going to take an extra page, so I left a blank page there. One more here. I'll have you guys do this one on your own. Ready? Go. What should dy dx be? The derivative of tangent 2t plus 2, which ought to be 2 secant squared 2t, divided by the derivative of this, which should be 1 over 3t cubed plus 5, and then times the derivative of 3t cubed plus 5, which was 9t squared. So this ended up being 3t cubed plus 5 times 2 secant squared 2t all over 9t squared. Everybody good with that?
Yeah.
Okay, and our second derivative then should be the derivative of that divided by dx dt. So the derivative of that, we'll have to use the quotient rule for. So 9t squared times the derivative of the numerator, which ought to be 3t cubed plus 5 times the derivative of 2 secant squared 2t, which ought to be what, 8 secant squared tangent 2t. Hopefully I did that right in my head.
Wouldn't that just be regular secant? Because you have to do the what's it called, power rule on secant.
Yeah, 4 secant. It's 4 secant 2t times the derivative of secant 2t,
Yeah.
which is 2 secant 2t tangent 2t.
Oh yeah, yeah.
So that's why it becomes a secant squared. Okay, so we got 3t cubed plus 5 times that derivative plus the derivative of 3t cubed, which is 9t squared, times the 2 secant squared 2t. And then, oh man, I've already run out of room here, haven't I? Wonder if it'll let me like move all this over. Oh, that looks weird. Anybody know how to make this like let me move it over? Perfect. It looks great. All right. So there's our v du minus u, which ought to be our 3t cubed plus 5 times 2 secant squared 2t. So u dv 18t divided by 9t squared squared. And then all of that divided by this 9t squared over 3t cubed plus 5.
No, because you already took the 3t. Oh, wait. Just kidding.
Yeah, just kidding. I did that right. All right. So, you know, then we can multiply the 3t cubed plus 5 up into the numerator of this whole thing and make this a 9t squared cubed in the denominator. You know, I got an 18 here and a 9 here. I could take out the 9 and cancel. I got the t and the t squared. I could cancel stuff out, but I'm not going to bother to simplify. This is good enough for the purpose of at least understanding what we're doing. Yeah. Or do you guys want to simplify?
This is very much is good for our purposes.
Yeah. All right. Everybody's good with not simplifying? I don't need you to simplify. If you want to simplify, you can. All right, cool. So let's find derivatives using polar coordinates now. Everybody good with the parametric ones?
Yep.
All right, hopefully so, because the polar ones end up being very, very, very similar to the parametric ones. Because what can I do with any polar equation? We'll say r equals some function of theta, r equals, sine 2 theta, or r equals 3 plus 8 cosine theta, or something like that. How can we rewrite any polar equation? X should always be r cosine theta, right? And y should always be r sine theta. And so if I had f of theta cosine theta for x, and for y I had f of theta sine of theta, don't these just look like two different equations that could be combined together as a parametric, all in terms of the parameter theta instead of the parameter t?
Yeah.
Yeah, they look just like that. So we should be able to, if we can rewrite r equals f of theta into terms of x and y, r cosine theta and r sine theta, we should be able to come up with dy dx is just equal to dy d theta over dx d theta. Right? And if you wanted to go through and actually figure out what each of those things was, we could say, I think I did this on the next page. No, I didn't. All right. It should be the derivative of y with respect to theta, which is the derivative of this f of theta part, which is dr d theta sine theta plus r cosine theta in the numerator. And in the denominator, it should be dr d theta cosine theta using the product rule, and then minus r sine theta. F of theta is just r. And you could memorize that formula if you want, dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. Or you could just remember it's the derivative of y with respect to theta over the derivative of x with respect to theta. So either one of these is fine, knowing this or knowing this. I think it's easier. I don't normally memorize this. I don't memorize that. I just know that it's this and do the conversion and call it good. But it's up to you. Does that make sense conceptually, how we can find the derivative of a polar equation?
Yeah.
Cool. And we should be able to say that again.
Conceptually, yeah. We'll see.
All right. Yeah, they get a little bit messy sometimes, but they're not too bad. I mean, they get pretty bad. So I was going to say something else about this. Oh, to find dr d theta, remember r is just a function in terms of theta. So dr d theta is just the derivative of that with respect to theta. So that should be easy to find if you need to. All right, let's find dy dx, the slope of the tangent line to r equals 3 sine 2 theta by turning this into a parametric. So what should we have for x? X should be 3 sine 2 theta, right? R times cosine theta. Isn't that what x is equal to for a polar equation? It's r cosine theta. And what is y? Y is r sine theta. Good or no?
Good.
All right. So if we want to find dy dx, we need to find dy d theta. So that'll be 3 sine 2 theta times the derivative of sine, which is cosine, plus sine theta times the derivative of 3 sine 2 theta, which ought to be what?
6 cosine 2 theta.
Excellent. All right, so there's our dy d theta all over dx d theta, which ought to be 3 sine 2 theta times negative sine theta plus cosine theta times 6 cosine 2 theta. Good or no?
Good.
All right, if you want to, divide everything by 3, but you don't need to. Easy enough. Noah, you all right with that? You conceptually understood before, but now you fully feel like you're confident in your ability to do that?
That looks great. Yeah.
Perfect. All right. Let's do this with another one. So what does x equal? Should be 3 plus 2 sine theta times cosine theta. And what does y equal? Should be 3 plus 2 sine theta times sine theta. Good or no?
Good.
All right, so dy dx or dy d theta over dx d theta ought to be just these derivatives. 3 plus 2 sine theta times cosine theta plus sine theta times 2 cosine theta. Everybody agree with dy d theta? And what should our x or dx d theta be? It should be 3 plus 2 sine theta times the derivative of cosine, which is negative sine theta. And then plus our cosine theta times the 2 cosine theta. Good or no?
Good.
All right, let's simplify this one down a little bit. 3 cosine theta plus 2 sine theta cosine theta, which is sine 2 theta, plus another sine 2 theta. And in the denominator, what do we have here? We have a negative 3 sine theta minus 2 sine squared theta. And then a plus 2 cosine squared theta. And so what does that become? 3 cosine theta plus 2 sine 2 theta. And then 2 cosine squared theta minus 2 sine squared theta ought to be 2 cosine 2 theta, and then minus the 3 sine theta. That one simplified down fairly nicely. Don't you think?
Yeah.
Yeah, that was a good one. That was nice. That was fun and or exciting. All right, you guys do this one on your own. Ready, go. What was x? X was 2 cosine 3 theta times cosine theta. And y was 2 cosine 3 theta times sine theta. Yeah. dy d theta should have been 2 cosine 3 theta cosine theta. And then plus the sine theta times the derivative of this. So that's going to give us a minus. It's going to be a minus sine theta times 6 sine 3 theta. So minus 6 sine theta sine 3 theta.
Yes.
All over what? Dx d theta, which should have been a negative 2 cosine 3 theta sine theta. And then plus the cosine theta times the derivative of this, which is going to give us another minus. So minus 6 sine 3 theta cosine theta. Everybody all right with that?
Yes.
All right, and obviously we could have, if we wanted to, divide everything out by a 2, but not necessary. Any questions on finding the derivatives of polar and parametric functions?
Will you have us completely simplify in quizzes?
No.
Can we actually go back to the last parametric that we did?
Last parametric, yeah. This one?
Yeah, sorry, where is the 9/2 squared over 3t cubed plus 5 coming from?
This is the divided by dx dt.
Oh,
Right, so-
okay.
Yeah, so remember our second derivative somewhere along the way here is the derivative of our first derivative with respect to t divided by dx dt. So this is the derivative of dy dx with respect to t, and then this is dx dt.
Okay, sorry, I forgot that you had to put the dx dt on the bottom.
Yeah, especially common mistake because people get all wrapped up in all of this stuff in the numerator that sometimes is really unpleasant, and then feel like, oh, thank God I finally finished it, and then forgot the divide by dx dt at the end. So yeah, just make sure you're careful with that. All right, how are we feeling? We feeling all right or no?
Great.
Wonderful. All right. We're going to take a 30-second break here while I open up the next thing that we're going to start with. All right. So next up, we're going to start talking about particle motion. And when we start talking about particle motion, we're just going to do a little bit of two-dimensional motion. And then we're going to move into motion in a plane using vectors. So you should all, with any luck, be familiar with the fact that the derivative of a position function is the velocity function, and the derivative of the velocity function is the acceleration function, and the derivative of the acceleration function is the jerk function, and the derivative of jerk is jounce, which is sometimes called snap, and its derivative is crackle, and its derivative is pop, and then lock, and then drop, and then shot, and then put. Right? Everybody remember that? Or at least these first two?
Definitely.
Yeah, derivative of position is velocity, derivative of velocity is acceleration, and derivative of acceleration is the jerk function, right? And another important thing that we need to make sure we remember when we talk about particle motion, especially in 2 dimensions, is that speed is equal to the absolute value of velocity. So velocity has direction to it. Positive velocity means you're moving to the right? Negative velocity means you're moving to the left, but speed is the absolute value of that. So if I'm moving to the left at 5 miles an hour, my speed is 5 miles an hour. If I'm moving to the right at 5 miles an hour, my speed is 5 miles an hour. And even more so this year when we get into vectors, speed being the absolute value of velocity is exceptionally important. So you don't want to forget that. And they love to put in questions about speed on the AP test just to mess with you and make sure you understand that speed is the absolute value of velocity. Speed has no direction attached to it. Good or no? Everybody good? Not good?
Good.
Great. Good.
So good.
Whoa, all right. So we've got a particle that is moving along a line. Its position at any time t greater than or equal to 0 is given by that position function, t squared minus 4t plus 3. We're going to go S is in meters and T is in seconds. We want to find the displacement of the particle during the first 2 seconds. So first off, the displacement. What is the difference between displacement and distance traveled?
Displacement from the origin, and then distance traveled is total distance.
Right. So displacement is not necessarily from the origin, but displacement is the distance from the starting point, right? Which may or may not be the origin. So in this case, at t equals 0, our starting point is actually 3, right? So we're not actually starting at the origin. So we got to be careful with exactly how we word things. But yeah, you got the right idea. If we're looking for the displacement, well, figure out where it was at 0, which is what? We just said 3. And figure out where it is at 2. And where is the particle at 2? Ought to be at 4 minus 8 plus 3. It ought to be at -1. Yeah. So what is the displacement in the first 2 seconds?
Negative
It's 4.
4.
Right, it's displaced 4 units from where it started. 4, what was it, meters? 4 meters, and we could say to the left if we wanted to be even more specific. Displacement is 4 meters to the left. What if we wanted to find the average velocity? How about velocity? Maybe we should fix that. Pretend that says velocity. Perfect, now it does. All right, how would we find the average velocity of the particle during the first 4 seconds? That ought to just be a change in position,
Position.
right? Change in S divided by a change in time. So that ought to be in the first 4 seconds, S of 4 minus S of 0 over 4 minus 0. And what's S of 4?
3.
3. And what's S of 0?
3.
3. So we end up with 0 meters per second, average velocity of 0 meters per second during the first 4 seconds. Well, that's telling us that this particle moved to the left some, and then it moved to the right some, and it came back and ended up exactly where it started. So the average velocity was 0. But if we want instantaneous velocity means we need a velocity function. And what is our velocity function?
2t minus 4.
2t minus 4, which we will evaluate at t equals 4, because that's what it asked for. I already wrote the t. Evaluated at t equals 4 gives us what? It's like 4 meters per second. So its instantaneous velocity is 4 meters per second. What about its acceleration?
Just be 2.
2. And if we evaluate 2 at t equals 4, we get 2 meters per second, or meters per second squared. Everybody good with that?
Oh yeah.
Wonderful. All right. Let's do one more of these nice, easy two-dimensional ones. So let's find the velocity of the particle at t equals 2, the acceleration at t equals 3, and with any luck, the total distance that the particle moves in the first 3 seconds. So how do we find the velocity? First, we need a velocity function, which is derivative of e to the 2t ought to be
2e to the 2t.
and then minus 4t. And if we're going to evaluate that at t equals 2, what do we get? 2e to the 4th minus 8. And what about the acceleration function? What's our acceleration function?
Four e to the 2t minus 4.
And if we want to know what that is at t equals 3, what is it? Should be 4e to the 6th minus 4. Everybody good with that?
Mhm.
All right, now it asks us the total distance traveled. Now we haven't done any integrals yet, so we can't quite figure that out for sure unless we know what about this particle's velocity.
The initial velocity.
Well, we don't need to know necessarily the initial. We just need to know that the velocity is always either positive or negative on the interval that we're looking at. And so what's the interval that we're interested in?
0 to 3.
It should be from 0 to 3. I don't know why this person's trying to get into the class right now. That's fine. All right, so from, what was it? Yeah, first 3 seconds, right? So 0 to 3. So what can you tell me about our function on that interval from 0 to 3? Hopefully that v of t is always greater than 0 on the interval from 0 to really to infinity. So if the function is always moving in one direction, if it's always got a positive velocity, then that should tell you that the displacement is equal to the total distance traveled. So we just need to figure out what is x of 3 minus x of 0 over 3 minus 0. So what's x of 3? E to the 6th, right? Minus 18 plus 2, so minus 16. And then if I plug in 0, what do I get? I get 1 minus 0 plus 2, so minus 3. And we end up with e to the 6th minus 19 over 3 units. Good or no?
Good.
Isn't there
Alright.
something like concavity when you do like the third part for the total distance? Or
Say that again?
do you have to do anything with concavity for this?
No. No, nothing with concavity. We just want to know what the displacement is, and since the function's always, since the velocity function is always positive for all real numbers, it happens to be positive. But specifically for from 0 to 3, all we care about is how far it traveled in that time. So nothing to do with concavity.
I have a question. If we're trying to find the distance traveled, is the 3 minus 0 on the bottom supposed to be like dividing by time?
Yeah.
Wait, why? If we're trying to find total distance, why are we dividing by time then?
Oh, good question. Why would I do that? Yeah, I'm glad somebody said something. That should just be the displacement. Not, yeah. Thank you. Get rid of all of that. There's no division there. Why would we divide by that? We're not looking for an average velocity. We are looking for the total distance that it traveled. Yeah, thank you.
Also, wouldn't it be for x of 3? Isn't it e to the 6 minus 18?
Minus 18 plus 2.
Ah. I forgot that.
Yeah, I at least did my arithmetic right. Any other questions on that? All right. So all of these motion problems and all of the motion problems that you might have done last year in my class, if you were in my class last year, were all done in 2 dimensions, right? A particle moving in a line. But we're going to open that up now and have a particle that instead of just moving in a line, moves in a plane. So instead of just being able to travel left and right, a particle could travel in an infinite number of directions, right? It could travel diagonally. It could travel, however you want it to travel. It could travel in some weird circuitous path, right? Particle could travel in any direction that we want it to in the coordinate plane. So it's still stuck in the coordinate plane. It's not going to like pop out of the screen at us. We're not going to do 3 dimensions here, but it could go any direction in the coordinate plane. Okay? And so the way we're going to deal with that is by introducing the idea of vectors. And vectors are very important to math and physics and all of that good stuff. And they're going to allow us to deal with particles moving in a plane. So there's just some basic information here about vectors. We're going to just sort of scratch the surface about what vectors are today, and then tomorrow we'll get into how to deal with them and how we can take derivatives with them and all that good stuff. So things you need to know about vectors. We're dealing only with 2-dimensional vectors, which are written with these angled brackets, which are called angled brackets, as A, comma, B, where A and B we call the components of the vectors. And a standard representation of any vector is just an arrow that goes from the origin to whatever ordered pair we have, A, comma, B, to whatever that point would be in the XY plane. So the A value is the X component of the vector, and the B value is the Y component of the vector. We call the magnitude of the vector the length of this arrow. This is the magnitude or the length of our vectors. The square root, and I don't know why that doesn't show the top of the square root there. It's the square root of A squared plus B squared, right? Because this is A, and this is B, and that's clearly, if I were to draw out the triangle, a right triangle, right? And so it ought to be the square root of A squared plus B squared using our Pythagorean theorem. That ought to be the magnitude of the vector, and we define the magnitude of the vector as the absolute value of the vector A, comma, B. Okay. So what would that tell you? And we'll get into this in a little bit, but what would that tell you about the speed of a particle if you were given a velocity vector? If this thing inside of here was a velocity vector, then the speed of that particle should be the
It's
absolute value of, right?
Positive?
Well, yeah, it's always going to be positive, right? Because speed is always positive. But it should be equal to the magnitude of the velocity vector. The speed of the particle should always equal the magnitude of the velocity vector, because speed is absolute value of velocity. We'll get more into that later, but just wanted to bring that up. There's a vector called the zero vector. The zero vector has no length and no direction, and it is written as 0, 0. It's just singular point there at the origin. And also, we want to talk about the direction of a vector. The direction of any vector is the smallest non-negative angle that we can form with the positive x-axis and the vector. So this angle right here is the direction of the vector. My vector was pointing out here, then this angle would be the direction of my vector. If my vector was pointing this direction, the smallest non-negative angle is this one, right? So we would have a direction of like 330 degrees on that, or 11 pi over 6 radians, something like that. Okay. So it's the smallest non-negative angle. We won't talk about direction of a vector as negative ever, or as something more than 2 pi radians or more than 360 degrees. Good or no? Any questions on these basic vector concepts here, these basic ideas about vectors? Everybody good? Everybody hoping I won't go to the next slide and I'll just stop right now since we have 1 minute left?
Yes.
Yeah, all right, so next slide. We will talk about tomorrow. That'll be good for today.